All right. Hello, everyone, and welcome to today's cryoEM Current Practices webinar, hosted by the three national centers established by the NIH Common Fund Transformative High-Resolution Cryo-Electron Microscopy Program. My name is Christina Zamani. I'm a scientist and training liaison at the National Center for Cryo-EM Access and Training, NCCAT. And today I'm joined by a panel of my colleagues from the centers who I'll introduce you to shortly. But just a quick overview, this webinar series is a regular event that we host to highlight the methods and tips and tricks that groups are using to obtain and interpret the data they can collect using National Center resources. And we typically meet the last Thursday of this month. The exception is November and December that we combine into one December talk. And this year we also decided to host a special event roundtable with a panel of experts in place of a traditional talk. But we will get back to our regular schedule on January 26th, 2023, with a talk from Dr. Hanbin Jeong, a postdoctoral fellow at Oregon Health and Sciences University, who will be telling us about a mechanosensory complex from C. elegans. But today we're actually here for a slightly less formal discussion. We polled our audiences during the past few talks, and there are actually many topics of interest. So we decided to pick a hot topic in data processing that we actually get many questions about from many of our users. And so we assembled a panel of experts. I'm going to have them introduce themselves briefly before we open the floor and have hopefully an insightful discussion today. First, I want to give a chance for my center colleagues, Ed Eng from NCCAT, Lauren Vega from the Pacific Northwest cryoEM Center, PNCC, and Michael Schmidt from the Stanford SLAC cryoEM Center, S2C2. They'll each give a brief update with any news from their centers, and then I'll turn over to our panelists. Finally, we are recording this meeting today, and we will post that along with all of our former talks onto our YouTube page, or you can also access these at the events page at cryoemcenters.org. We will take questions through the chat, or since we're in a meeting, you'll be able to unmute yourself and ask questions live, but we'll ask people to raise your hands and we'll call on people to ask questions to make things a little more orderly. So please just use that raise hand, or feel free to toss questions in the chat and we can help moderate that for you. And so before I let our panelists introduce themselves, I'm going to turn over to Ed to let us know what's going on at NCCAT.
Okay, NCCAT's here in New York City. We offer high-end instrument access, grid preparation and screening, as well as cross-training. April 10th through 14th, we'll have our one-week tomography short course in conjunction with our sister center in situ. Applications are due January 1st. So if you're interested, find out more at nccat.nyspc.org. Back to you.
Thanks, Ed. Lauren?
Hi, everyone. So at PNCC, we are accepting people for on-site visits. We have started our screening access proposal visits, and we have them going all the way through March of next year. And our general access proposal types that is up to 20 days a year of access is also available. We have all of our instruments up, and we're currently waiting for our Vitrajet to come back from overseas, fixed and very useful. With that being said, we have, I think, our sample preparation and our data collection workshops at the beginning of next year. If you want to start looking for registrations, those should be coming out in the next month or so.
All right, thanks, Lauren. And Mike.
Hi, I'm Mike Schmidt from the Stanford SLAC cryoEM Center, and we have 3, now becoming 4 Krios microscopes and a Talos Arctica and soon to have a Tundra. We have all the specimen preparation equipment, including Chameleon, and soon to have Vitrajet. We're our next workshop will be a data processing workshop in conjunction with the group in Madrid, who will be telling us about Scipion and how that packages all of the different data processing pipelines into one group. We're accepting, of course, on-site or remote data collection and training and screening. Please join us. Bye.
Thanks, Mike. So I will stop sharing. And do feel free to turn on your video if you want to feel like you're in the room. I see lots of gray boxes on my screen, which is extremely exciting. We're glad so many of you joined us to talk about this today. So I'm just gonna call names from our panelists, and I've asked them to sort of prepare a 2-sentence introduction of who they are for those of you who don't know them yet, and their experience with particle picking with neural network pickers. So Patrick, I'm gonna let you go first.
Hey, good morning, everyone. My name is Patrick Mitchell. I'm Director of Operations for the Stanford SLAC cryoEM Center. My expertise is primarily in instrumentation and applications and getting the data. So for most machine learning questions, I'm going to defer to our resident expert, Muyuan Chen, who has years of extensive experience in machine learning and in neural networks. But if there's any specific questions about our operations or the way that we're applying things here, I'm happy to address those.
All right, Amy.
Hello, everyone. My name is Amy Liu. I'm also a cryoEM specialist at S2C2. So most of my work is to train cryoEM newcomers and to troubleshoot the problem they have from sample prep to imagery processing. So I have some experience about Topaz, and I would like to discuss with you in this roundtable discussion.
Thank you. And Muyuan?
Hi, I'm Muyuan Chen from S2C2. Yeah, right. Yes. I think, yeah, I the only experience of particle picking is that I wrote the thing in Eman2, the neural net picking in Eman2, and well, and subtomogram picking if that's topic 2. That's about it.
That's about it, but that's pretty big and makes you an extremely valuable member of this conversation. So we're very pleased you're here. All right, Tristan.
Hey, yes, I'm Tristan. I'm the machine learning group leader at NYSBC. Before that, I was a PhD student at MIT. I developed Topaz, and so Topaz is a neural net-based particle picker that uses positive unlabeled learning. Yeah, thanks for inviting me.
Thank you. Craig.
Good morning, everyone. I'm Craig Yoshioka. I'm one of the co-directors at the Pacific Northwest cryoEM Center. I've been doing cryoEM for a while and dabbled in pretty much every aspect of the technique, including research, software development, infrastructure, and then help setting up, building, and running a large cryoEM center. When it comes to neural network particle pickers, I've only been a user of them. But I like to try every new toy and tool that comes out to see what can be done with it. Thank you.
Thanks, Craig. And Vamsi.
Hi all, I'm a microscopist at PNCC. My role is basically talking to users, helping them with data collection, analysis. I've used a couple of particle pickers, and my view is very similar to what Craig said. I like to test and try everything that's available. My extensive experience has been, of course, with Topaz, and Topaz is amazing. So yeah, there you go.
Great. And so now the floor is open. So while everyone is sort of formulating what questions you have, maybe typing them in if you don't want to unmute yourself, or if you're ready, feel free to raise your hand. We'll take the conversation in the direction where people have questions. a quiet room so far. So I actually have a question. I'll start up with a question for Craig. So Craig, you said you like to dabble, and I would say at NYSBC we have a bit of a bias towards Topaz. But I guess you've probably dabbled in multiple things, and so what would you say are the biggest differences practically between using the different neural network pickers that are available?
That's an interesting question. I think the boring answer is just mostly in setting them up and figuring out how to get them to work. And then they all behave a little bit differently, right? But that's more a matter of like what works best for your sample. And honestly, a lot of things work really well for a lot of different samples. And so it's primarily just becoming accustomed and comfortable with the tool that you do want to use, and learning to master it, and maybe learning where its strengths and its weaknesses are. But that'll takes a little bit playing with your actual data set. Yeah, sorry, there's not a really sophisticated answer. It really is all about how complicated sometimes it is to get it going. And I think a lot of people give up at the point where like they just can't get a piece of software installed and set up and running. I think that's where a big activation barrier is actually.
To that point, what if you go through each one of them, what is the minimum required hardware and software environments for setting up one of these things? Is it also involved in the actual pipeline of data collection so that images go straight to the particle picker, or do they get processed offline after the data is collected? That's one question. We do have a question from the let's get through first. Okay, how to set them up? Go ahead. How about you start, Tristan, and we'll say, oh, how do you set up Topaz?
Yeah. So for Topaz, we provide a couple of different installation methods. Yeah, this has been a big question, that especially in the early days of Topaz, when we didn't have sort of like nice build systems, that we would get a lot, because it is annoying to like set something up if you have to install it from source or something like that. So Topaz is available on like pip, so you can pip install it. It's also available on Conda. If you have Conda like Python, you can install it that way. You can also, of course, install it from source by cloning it from GitHub. The installation instructions are not too complicated if you do want to do it that way. It's also available on what is the software repository that's managed, I think, by Harvard? I'm blanking on what it's called right now off the top of my head, but it's also available there.
SVGrid.
They have a repository. Yes, SVGrid. Thank you. It's also available on SVGrid. And also there are plugins for Topaz into Relion and CryoSpark, but they, there is integration there, but they do require you to install Topaz separately. So you would still need to like Conda install it or pip install it into some environment for those.
We do have some questions in the chat as well, Tristan, when you're done.
So I think that's how installation works for Topaz at least.
How do you teach people how to do the CUDA and all this GPU installation?
Yeah, so you would need to already have CUDA on your system. Actually, there's actually some nice ways to install CUDA now that are a lot easier than they used to be. It used to be a huge pain if you didn't have CUDA already to install it, but actually now you can install CUDA directly through Conda.
Oh, yes.
Which makes it a lot easier if you don't already have a system, with CUDA pre-installed, or who like, a IT team who set that up for you basically. So you can actually install it through Conda. Makes it a lot easier.
Yeah, I'd like to add that does make it a lot easier. I think the only barrier now is NVIDIA drivers, which require
root the driver you can't.
Yeah.
Yeah.
I actually have a question for Tristan, if that's okay. Is there a standalone version of Topaz? I believe there is.
There is.
Okay. would be really nice if that is marketed as a standalone version, because I believe everybody wants to use Topaz inside Reliant or CryoSpark, but
Yeah.
having it as a standalone version would give us the flexibility to not have to work with the integration into Reliant or integration.
Yeah, no. Topaz is completely standalone. If you like Conda install Topaz or whatever, you get the standalone version. I do think most people use Topaz now through the CryoSpark or rely on like plugin integration, as far as I can tell, but it is 100% entirely standalone. The drawback of the standalone version of Topaz is there's no GUI. Okay, there's a rudimentary GUI, but it's primarily command line. So there are instructions if you go to the Topaz GitHub and look at the README. And we also have a sort of brief tutorial there on like using the Topaz command line tools to run Topaz. And there is also a bare bones GUI there, which is basically a web-based GUI, mostly just to help you label particles. It doesn't actually run it for you. It'll generate commands. That's something that I think has been on the development list for a while, is to maybe actually also build a standalone GUI for Topaz, possibly as like a Nepari plugin or something like that. But unfortunately, we don't have anything like that right now.
Do you want to get to some of the questions in the chat from our participants that are in the meeting? We do have a question. Is there a version of Topaz available for particle picking in tomography?
We do have a beta version for tomography that is not public release yet, because I think we're still doing some testing of it and want to make sure it works well before we like release a new Topaz version with that in it. But the answer is yes, we do have a beta version. So if you're interested in trying it out and are willing to potentially suffer through some, you want to help us beta test it, feel free to reach out to me. But I think we are hoping to get that released in the next few months, basically, with the next Topaz update.
Muyuan, you mentioned that the EMAN version of the particle picker is in fact able to pick things from tomograms. Can you describe that a little bit?
Oh, yes, that thing has been there for a while. I mean, there's a E2SP Boxer ComNet or something that you can find through the project manager GUI that let you go through a number a whole entire data set of tomogram and pick particles. I mean, it's been there. It's just if you're using Reliant or IMOD or something, it's not integrated. So.
Another question in the chat is how to decide which model to choose for particle picking, like RasNet, 814, etc.
Is that question specifically for the model options in Topaz?
I believe so, specifically for you as well, Tristan.
Okay. Sure. Yeah, so this is a little bit of a your mileage may vary kind of question and answer. In my personal experience, basically a lot of it comes down to how complicated your particle is and how many labels you have. If you've labeled more particles, or if you've done something like, something that I think has been pretty popular now in terms of how people use Topaz, is you first run either the Topaz general picker, or you run some sort of template matcher or difference of Gaussians, and then filter that very stringently, and then you use that to train a Topaz model to basically expand that out into your a full set of particles. In that case, you probably have a larger set of labeled particles. And when you have a larger set, then you can use one of the larger models. So in that case, you can go up to the larger ResNet and get good performance, right? It'll give you better performance than in the smaller ResNet because it has more parameters. But on the other hand, when you have a smaller data set, or if it's something where, maybe, you went through and you labeled 100 particles, then you probably want to use the smaller ResNets. I pretty much always recommend using the ResNets. In my experience, the regular comms, we provide them mostly for posterity, but they don't really perform better. So the smaller ResNet then would be what I would recommend as the go-to, but you can always cross-validate it. I think that would really be the gold standard, is like train each one and then take a look at some evaluation metrics on a sort of held out set of your particles and see which one works the best. But I think, yeah, there's many things that would be nice to add in future versions of Topaz, but probably a way to auto like this would be one. But I don't think it makes it's not too hard to mess around with it a little bit, I think, and that's sort of the rule of thumb, though. I think more data equals bigger model is more likely to be better. Less data, smaller models probably likely to be better.
Oh, hi. Do anyone has any way to pick filament nicely? Particularly as filament, including the direction and those things.
We don't have anything built into Topaz for that, at least not for directions. I mean, I think what some people have done is like label, if you can label the two ends of your filaments, you could,
if
maybe
you
try to
pick them
those
as individual particles. I think getting them to the bright spot is easy. To trace them together into an individual filament is tricky.
Yeah.
Just curious if there are any tools around.
So there is, Shores actually did put out a patch for Topaz that included some filament picking support that they've been using. We haven't upstreamed that yet. That's also on the radar for hopefully like the next version release of Topaz. It doesn't, so I think it would basically take this approach of like tile picking and then tracing. But I don't know if it can do orientations. Actually, I'm not sure it can do like plus minus orientation. It mostly just looks at
I try to get a statistic of the length of the segment and the direction, and it's by definition NP hard, right? If you have
it's a hard
segment.
problem. So we've been doing some research on like this problem as well, and I think hopefully basically focused on like, if you tile pick up filaments, can you then like segment them into the individual filaments, especially when you have like filaments overlapping each other and stuff like that in micrographs. But I can't say anything concrete about like a release date for that in Topaz.
Do anyone hear any other software that does it?
I'm not aware of any specific one. I mean, there's like multi-curve fitting. Cryolo has some support for filaments as well.
Oh, right. Yeah, I think I heard about it a bit.
I think we have a question that'll prompt a lot of people on the panel as well. Given the numerous machine learning algorithms, ePicker, DeepPicker, Sphere, Cryolo, Topaz, for the cryo-EM particle picking, how does the panel decide on which software to use? Do you try them all and see which one gives the best result downstream? Or is it that the panel has suggested it really depends on how easy it is to install and run the software? I'm going to pick on somebody that hasn't talked. Vamseedhar.
I think after a point of time, all particle pickers do really well. It really depends on what kind of protein you have, how difficult it is to work with. Sometimes proteins can be very difficult to pick. Once you're able to, I mean, if it's a generic protein or a more easily workable protein, it will end up being picked by a neural network picker, a particle picker. But the idea of most neural network pickers is pretty similar. They use these machine learning algorithms where they're looking at, something called as edge detection, where they're looking at the edge of the change in the contrast of that particular particle. And if there is enough signal in there, if there is enough differences in that contrast, your neural network picker should work. Now, if you talk about the installation process, that is that's become a lot easier now compared to 3-4 years ago, even 3 or 4 years ago. So I mean, if you can get it to install it, you should try all of them and see which one works best for your protein. Most often, all of them will work really well. Some have some extra features, like we were just talking about the filament picking. Some pickers don't have that, some pickers do. which is fine. Now, there's another aspect to this too, the installation process. If you are at a university or if you're at a large institution, you most often have a centralized resource, an HPC, where all of these are installed and ready for you to go. So if they're already installed, just use it. And if you have the time, then get a Linux box, just install it yourself and get it running. It's not that difficult to do.
Any dissenting opinions in the panel? Dun-dun.
I'll just comment, we definitely rely on the experience of, power users who love to try out every single algorithm. So it's not reasonable to expect every user to try every program on every PC. And so, if a new option comes out and one of our users has tested it, we'll ask them to do either a group meeting or a journal club to kind of give us an overview of their experience, what they saw as the advantages and disadvantages, and if it's a program that they would recommend to people with specific problems or specific applications.
Yeah, I don't know if it's a dissenting opinion. I'd like to add that, at least myself, I take a really pragmatic approach to most of processing, which includes particle picking. And if something new comes out and it's cool, I'll download it and try it. But for just most data sets, and I've looked at quite a few, it's you just crank the wheels. And if you look at the output and you see if there's a problem, and that's the real trick, is trying to figure out, train people to recognize when there's a problem in their data set and correctly attribute that problem to, for example, particle picking. Like the most classic one is seeing like a not a very even orientational distribution in your 3D reconstruction. And so you think, do I have a preferred orientation, or was my particle picker biased? And that's generally when you start going back and trying to see if you can do a better job at particle picking, whether the particle picker you used was too biased and you need to loosen it up and make it sloppier to try and pick up rarer classes or pick up orientations that were just missed completely. And so for me, it's always been use the tools well, get to the answer, see if you need to go back and tweak or explore alternatives and for something like particle picking, and work from there. So like Vamsy said, I feel like most of the tools can be made to work well for most data sets, but some will definitely be better suited. And if you look at the same thing, every, multiple data sets over and over again, solving the same complex or the same set of proteins in different complexes or with different drugs, yeah, you should probably use invest a little time in training a deep learning particle picker to be discriminating and fast at picking that particular sample. Yeah, that's the only advice I have.
I would actually like to add to what Craig said too. One thing that I've done, at least personally I've done, is when I look at a data set, I'm going in with some sort of a very generic picker, like a blob picker, to just pick blobs, as many blobs as I can get. Once I have all of these particles, once I have all of these particles, then I'm doing extensive 2D classifications. And once I have a very small number of very good particles, that is what really determines how well your neural network picker will work. And when you're picking these subset or very small number of particles, you don't really need that many, but you definitely need as many orientations of the particle that you can get. And that really will determine your final model quality also.
So I get the impression that all of these neural net pickers are iterative, that you pick once and you it's not you only look once. It is you pick once, you get some small set of classes that seem to represent the object you think it is, and then you do it again. You use that as to create a model for the next round of picking, Is that the preferred way of doing it? As an iterative process where you do several rounds of looking at the original data more than once, with more than one kind of criterion. Is that a fair statement?
I think the final particle picks that go into the neural network, so it's pre-neural network particle picking, I think that's where you're trimming down your initial particle set, because that's, I mean, if you put in garbage, you get garbage out, right? So you're trying to put in as many good particles as possible, as many orientations as possible, and that's how your model also gets trained on those. So your pre-neural network picking makes a difference, and sometimes you can't get a blob picker also to work. You could actually just go and pick manually, although manual days are long gone pretty much. Yeah, being the pre-neural network is just as important as the neural network model.
That actually kind of brings up another question in the chat, is how do you decide between optimizing the particle picking neural networks versus optimizing the sample preparation or grid freezing component for cryo-EM?
Yeah, I was actually going to say this dovetails into that, and it's an incredibly difficult question we could spend like years talking about. And I feel like we've touched on it a little bit, but I wanted to actually like send that to Amy and see if you had anything to contribute to the conversation already, because I know you work with a lot of different users. So what are some of your tricks for when you make that decision?
To tell you the truth, if you see pre-fermentation, your 2D class averages, the first thing I would like to try is to optimize your samples. If your sample can be optimized, then you save a lot of efforts in the downstream processing. Of course, you can do some tricks like tail data collection, or you can use neural network to tune it to see if you can get many views as possible, but that's not guaranteed. So what I will suggest, if it's easier to get you to work on the protein, get back to the bench, and then try to optimize the sample. But if we try a few rounds and then doesn't really see an improvement, then yeah, I will try to do some tricks in the downstream processing to see if it's gonna work or not. But again, it's it's, as you mentioned, it's very hard to decide which way to go. So sometimes you got to try both.
Mm-hmm. Okay. There's another question in the chat about particle picking for long objects, not linear, not filaments, but large axial ratio objects. I presume that means. What are the issues in getting particles that depending on the orientation could be looking very long, and other orientations that could be looking very narrow because you're looking down the long axis?
So when we were first working on Topaz, actually, we had a particle exactly like that was sort of one of our test cases. And it actually does, the network is able to center the particle pretty well, in my experience. I think also this particle was pretty heterogeneous in terms of like so it was a long axis particle. So if you have the top view, it basically looks like two dots because it has these sort of two sticks that are joined at the ends. And then there's some heterogeneity in sort of the spacing of those. And it looked like, from our experience, it centered pretty well. I don't know if, say, like a blob picker didn't work for that particle at all. So I can't, in that sense, I guess it centers very badly. I'm not sure how well a template specific sort of approach would center that. I think this one was a little bit too heterogeneous for a template to work very well. But that's not to say you could maybe come up with like a set of templates that might get the job done. But in my experience, the neural net pickers actually give quite good centering. One sort of trick for centering, by the way, in Topaz at least, there's a parameter when you train the network called radius. And that parameter sort of sets this like blob factor around where your actual pick locations are when the network is trained. So it tells the network, hey, like label everything within 3 pixels of that center as a positive. So if you set that, if you fiddle with that, you can sort of increase the sharpness of where the network thinks the center of a particle is. So if you set it too small, it can cause training problems. But there's some things you can fiddle with there to try to increase the centering. I think the other factor is any kind of retraining procedure that sort of like shrinks down to the center could also improve centering.
As I posted in the chat, just do 1 round of refinement and you re-extract it based on the center, and maybe use your own refinement result to do the template. It might work.
There's a specific question in the chat regarding the EMIN2 for neural network training. And they're wondering if your feature is interested in a small, if what you're looking for is small, is it more advantageous to decrease the box size around it or to just optimize your manual annotation, or both?
Oh, yes, I missed that one. As long as it's bigger than say 4 pixels or something, it should be fine. But reducing box size shouldn't hurt that much either.
Yeah, I just wanted to pop in and say, I'm guessing a lot of you here in the room, even if you're not on our panel of experts, have some experience. And if you have, you know, your own experience to share, feel free to raise your hand and we'll let you pipe in. We are a community and learn from each other. So don't be shy if you've tried all the pickers and only one works. That is useful for all of us in the room to know and talk about. So feel free to raise your hand for comments as well as questions.
I have a question. This is for Tristan, but also for all the panelists. With Topaz, what this is the computational aspect of it. What parameters are you choosing, and how long does each job take? Let's say you have 10,000 particles that you input into the model. How long should that technically take? Because I've seen people run Topaz jobs that run for like 10 hours, which is terrible. And I have optimized it in my own way, and I've been able to run a Topaz job in under an hour, and the same job. So I'm wondering what's the logic behind it, and how do you get to that?
So I can give you the practical answer, and I can give you what I think is the correct answer. So the practical answer is you probably don't need to run training for that long most of the time. Like you can run it, you know, for an hour, and it's probably going to be just as good as if you ran it for 10 hours. In fact, if you ran it for 10 hours, you might get into trouble because, you know, if you didn't provide a lot of labeled data, the network could start to overfit. So from a practical perspective, I would say, like, especially if you're using starting from one of the pre-trained Topaz models, which I recommend doing, the network will train very fast. So what I would recommend doing in that case is ideally you would have you have your training set and your validation set, and you would actually look at the outputs coming from Topaz and track the performance on the validation set. And if it doesn't, you know, once it stops improving, you just stop. You're done. There's no reason to continue. And if it starts to go up, you should definitely stop. In fact, you should have already stopped. So from the perspective of what's correct, that's what's correct. So really what you should do is have this holdout set and monitor the performance on that holdout set and stop when that doesn't improve anymore.
And saying that, why don't you do early stopping criteria based on tested performance then?
So it's controlled from externally, right? You can do it, but it's
just
because we don't require a user to
stopping.
provide a validation set.
Oh, okay. have you tried this validation set and early stopping criteria? Do you have something recommended?
Yeah, you should do it.
Good.
Yeah.
Do you stop when
recommended.
do you stop when this validation lay flat, or you wait for a while, or you wait until it rises?
If it flattens, you can stop immediately. It can be hard to tell sometimes because there is stochasticity in it though, right? So like as like a general rule, what you could say is if the validation loss doesn't improve after like 3 epochs, then, stop, something like that. The Topaz will also save the network every epoch. So you have access to that full history. So because of that, you can stop and sort of roll back to your best network and then go from there.
We have another question in the chat. Like, what are the important criteria to look for in order to compare particle picking results or programs?
That's gotta be really hard without ground truth data.
So my personal opinion on this is probably not what most people like to hear, which is, well, you should hand label a bunch of particles and then you can directly compare the performance based on how well the networks are able to actually recover those when you hold them out. And that would be that's like the gold standard. Since most people don't like doing that at all and avoid that entirely in their frameworks, it's sort of hard to say then. I mean, you can still form validation sets, and in principle, that's probably the best way to evaluate. I think, of course, you could run the whole process, go to your structure and then decide if you like the structure better. But that's, pretty arbitrary, frankly. And may not actually reflect the performance of the picker.
Yeah, I think most often the issue is a systematic bias that you're missing some views entirely, and in that case, you won't be able to figure out this validation or even handpicking, because like the Tristan's 2-dot example, sometimes humans just you don't recognize that 2-dot is a particle top view, right?
Yeah, that's the problem. But I think on the other hand, if you try to evaluate based on the resolution of a structure, then you run the risk that, let's say a particle picker that's actually retrieving more conformations of your protein may not necessarily give you a higher resolution structure, but actually it's doing better. It's just that that's a failure in the reconstruction step. And so it's hard to say. I don't know, you could maybe look at your orientations that are present in your structure or something like that. And if you have a better covering of orientations, then you could say that picker is probably doing better, but then you should also probably get a high resolution structure. But
so the one question, this goes back to the question is, how can you tell if it has failed and or done a suboptimal job? Let's say that it won't completely fail, but how do you recognize suboptimal performance, and how do you ascribe it to particle picking versus some other step in the process? I presume that you can recognize this structure just doesn't look right. Do you look especially at the Euler angle coverage and say this kind of particle picker picked particles in a particular kind of orientation and left others out, and that's a sign that you need to go back and pick more particles, or as Amy said, go back and make better specimen preparation. But at least you would recognize that some orientations are overrepresented, either because they are or because the particle picker has just chosen those. What is your criterion for recognizing suboptimal performance? That goes back to this question again.
I think that's something probably practitioners should answer.
Yeah, Alex, did you have an opinion?
Yeah.
Alex, go ahead. I see your hand up. Oh. Yeah. We can't hear you. You're not muted, but we're not hearing you.
Run over to Christina's room.
I'm upstairs.
Oh no, I was kidding.
Oh, I think he might find Tristan first.
Yeah, he can. Here.
Okay, I don't know where Tristan is. I think there's an answer to this ground truth problem.
I have headphones, so
Oh, go ahead.
yeah,
We can hear you though.
yeah, but you can't hear them.
That's okay. Okay, can you hear me?
Yeah.
I think there's an answer to the ground truth problem in general, which is just do some tomography on your single particle sample. You will get known orientations out of that, ratios of different orientations, potentially large conformational variability and compositional heterogeneity. And you'll maybe be able to see, is your particle breaking up? You'll get information on air-water interface. So you'll get some ground truth out of that. You'll be able to see, are your particles overlapping a ton? And that can be contributing to your particle picking issues. So I always recommend doing tomography, and people virtually always do not do it.
Well, I saw your comment, Alex, and I was thinking like, no one has time to do that for getting their map, but your point about doing it for ground truth and developing and validating particle pickers, that's awesome. Yeah, I think that's right on.
Yeah.
Makes a lot of sense.
The great part about that is that the relationship between different orientations is preserved in the tilts. So you know that this same particle, which the particle picker picked it at 0 degrees, it didn't pick it at 60 degrees, and it should have picked it because it's the same particle, and it should pick it in those different orientations. That's actually very useful, and it could be good for testing, as you said, testing the algorithm, even just tilt pairs.
Pairs is mostly for validation, right? It's hard to do a refinement of tilt pairs directly, or
Yeah.
someone is doing already.
No, I agree that this is perhaps even.
I mean, you want the orientation distributions. That means you kind of have to have many particles and to form a histogram or heat map or something.
Mm-hmm.
I have a question for the panel, if we have time. Do we have time? What do you think of using deep learning to do something like building a taxonomical classifier tree for something like template matching, like Nico does? So rather than brute forcing it, he's searching tomograms, or not tomograms necessarily, large field of areas to find all the different particles and assign their orientation and depth. And it's very brute force approach. And I've always wondered if it's feasible, and I don't know the answer to that, if it's feasible to rely on training a neural network to make that job more computationally tractable. Because you could feed the network 3D orientations of all kinds of structures from the PDB. There's no noise problem. It's just more about building some kind of classifying tree that's more computationally efficient. I don't know if it would work or not. I'm curious to hear what you guys' thoughts are.
I saw Mingxu here. Is that right person?
I guess my take on this is maybe. I think so. The thing with what like Nico's particle picking or like template matching work is that they're trying to estimate those parameters, and so it's basically just doing a brute force search over possible defocus values, possible orientations of this particle. But in that sense, like it's more closely related to what's happening in reconstruction, I think, where we also do a brute force search over those parameters. If you're going to do a CTF refinement or estimate the angle of the particle in a reconstruction, it's the same problem. I mean, in that sense, maybe what Nico's doing could benefit actually from taking more of a page out of things like the approximations in the reconstruction work for that, like branch and bound, right? If you're trying defocus values, that's a single scalar value that you're searching. I don't know if that's convex. So for one thing, the actual optimization properties of that, I'm actually not sure. If it's convex, you
you could efficiently search it. You could apply sort of like a scalar convex solver actually to it to try to find the optimal value of it without brute force searching a lot of values. And it's, which should require you to test a lot fewer. For angles, angles are non-convex, right? So that's the hard thing with angles, but something like branch and bound as an approximation maybe, could still be helpful, because you basically template match at low resolution first, and then you only sort of expand out in high resolution, sort of like the regions where it looks like you have good angular matches, and then that also is a lot less computationally heavy. So maybe some things like that. A neural net doesn't really have anything to do with it. Maybe a neural net could come into that somehow, but I think there are other algorithmic tricks that could be used.
Yeah, I guess I'm glad you brought up branch and bound, because it kind of gets to what I was thinking of is, would it be possible to use a neural network to train a more biased branch and bound sort of classifier? But yeah, anyway, that's sort of, yeah, okay.
But Craig, I have a question for you. How does that how can that model be used for future data sets that are going to be collected? Like, if there let's say you have an APO protein, you have a single protein, and then you have a complex of the protein with another protein. How does the neural network has to be diffuse enough to be able to accommodate that into the picking, right? But then if you apply it, if you make it diffuse enough, then does it actually train well? I don't know if I'm asking.
I think it's a different application. You're not trying to find unknown things. You're trying to find from a library of known things, find the position and associations.
But eventually, what's the use of doing that?
That's
like,
is it an expedition?
Okay.
Yeah.
Okay. I was wondering if you're creating sort of a library of this magnitude, then it should have a use case in future data sets too, right?
I do think one of the big problems with sort of any concept around having your neural net picker try to do something like predicted defocus, right? I mean, you could think about trying to have the neural net explicitly try to solve that inverse problem. I think is that maybe defocus is possibly slightly more doable, but like orientation angle is entirely dependent on sort of what else is in the sample. There's no sort of fixed angle that is the correct answer, and that's why, there might be some ways to sort of get at that problem, but I'm not sure I don't think it's extraordinarily straightforward, and I think those networks will probably be prone to not generalize super well, would be my guess, but maybe there's a way to formulate it that it would.
For all of our listeners, I threw up a poll asking how you liked this roundtable that we did today before everybody kind of starts leaving as we get closer to the end of the hour. If you guys want to navigate to that poll, it's at the bottom of your screen. But I want to go back to some of the older questions that we had that we still haven't answered yet. So we have 3 questions about Topaz. So someone's curious if you can use Topaz while you're doing on-the-fly CryoSpark Live.
Practically, no. I don't think there's integration in CryoSpark Live like that. In principle, we probably could, but Topaz does have a general picker. I think in general, like that works fine if you're doing like very standard particles. If your particle is not a very standard particle, you need to train the network. So, we don't have a way right now to train the network fast enough for it to make sense sort of like in an on-the-fly processing setting. I mean, maybe you could label particles on your first couple of micrographs and then train a network, and then you could take that network and go and, automatically annotate stuff. And if you're still collecting, it could run on those. So I don't know that the issue is licensing, because Topaz is, well, okay, they don't want to include GPL-v3 code inside the CryoSpark source code, but you could still run it as a command line tool, which is what they do for their other integration. Anyway, that's a side point. But so I guess the answer is like, I think it's something that could be done, but it just hasn't been built yet.
And then we have another Topaz specific question. When we use the best particles from 2D averages and then try to train a model in Topaz, is it going to pick the missing views too that are missing in the 2D averages?
That is probably not. It has some fudge factor there, right? Where it can get views that are, slightly off, right? It'll still get those, sure. But if you're like radically missing some entire view, like you only have top views of your particle and you want Topaz to pick orthogonal views, it probably won't. I mean, it depends on your protein. If your protein is like, has some symmetry or, well, then you wouldn't have this problem anyway, right? But, or is roughly globular, yes. But if they're very, very radically different looking, and one of those views is entirely absent from your sort of training data, then probably not. Topaz doesn't really like internally have a 3D representation of your particle. So, and even if it did, if you were missing those, there would be no way to sort of fill that information in anyway. So, no.
Yeah, and maybe it's a good chance for if any of the panelists have any final thoughts you want to share. Otherwise, we'll wrap up so that everyone can get to where they're going. This has been a really fun discussion. I think it turned into a lot more about particle picking generally than anything else, which I think maybe says something about how ubiquitous this neural network picking is in particle picking. That is just part of particle picking. But yeah, I'll if anyone has any last thoughts, otherwise we'll wrap up and see you all back in January.
Thanks, everyone.
Yeah,
Feel free to hit that poll on the way out.
Yeah.
Yeah, I have just one last thing to say. If you're using a neural network picker, garbage in, garbage out. Just remember that. Don't put garbage in, you will not get garbage out.
Very true.
Thanks, everyone.
Words of wisdom. Yeah.